In 2022, the James Webb Space Telescope pointed its golden mirror at a tiny, almost negligible sliver of deep sky. What came back was impossible. Galaxies. Bright ones. Massive ones. Galaxies that appeared to have assembled themselves into mature, luminous structures within just a few 100 million years of the Big Bang. Standard models said this should not happen. The early universe was supposed to be a dark, formless place where gravity had barely begun pulling matter together. Instead, Webb found cosmic cities already glowing where there should have been nothing but scaffolding. The first galaxies did not arrive when we expected. They arrived earlier, brighter, and more developed than anyone predicted. This is the story of what that means. If you enjoy journeys that change how you see reality, consider hitting that like button and subscribing. It genuinely helps this channel keep making these deep dives. Now, let's begin. Before a single photon from the James Webb Space Telescope reached a scientist's screen, astronomers already knew what the first galaxies should look like. They had spent decades building that prediction. They had run thousands of computer simulations, written hundreds of theoretical papers, calibrated their expectations against every scrap of data the Hubble Space Telescope could provide. The picture was elegant, internally consistent, and agreed upon by nearly every major research group in the world. The first galaxies were supposed to be small, they were supposed to be faint, they were supposed to be messy, shapeless clumps of gas and young stars struggling to hold themselves together against the radiation pressure of their own newborn suns. Nobody expected cathedrals. Everyone expected huts. To understand why that expectation existed and why it seemed so reasonable, you need to understand what the universe looked like before those first galaxies appeared. And that means going back to the beginning. Not the beginning of galaxies, the beginning of everything. 13.8 billion years ago, the universe emerged from a state of almost incomprehensible density and temperature. In its first fraction of a second, space itself expanded at a rate that defies human language. Temperatures were so extreme that matter as we know it could not exist. No atoms, no molecules, certainly no stars, just a screaming hot plasma of fundamental particles and radiation, expanding and cooling with every passing microsecond. Within the first 3 minutes, protons and neutrons fused together to form the nuclei of the lightest elements. Hydrogen, helium, trace amounts of lithium. That was it. The entire chemical inventory of the universe at 3 minutes old consisted of 3 elements, and roughly 75% of that inventory was plain hydrogen. No carbon, no oxygen, no iron, no silicon, nothing you could build a planet out of, nothing you could build a molecule of water with, just hydrogen and helium drifting through a rapidly cooling fog of radiation. For the next 380,000 years, not much happened that would look dramatic to a human observer. The universe was opaque. Photons could not travel any meaningful distance without slamming into a free electron and scattering in a random direction. Light existed everywhere but illuminated nothing, because it could not move in a straight line. The entire cosmos was a glowing, featureless fog. Then something changed. As the universe expanded, it cooled. When the temperature dropped below roughly 3,000 degrees, electrons slowed down enough to be captured by hydrogen and helium nuclei. For the first time, atoms formed, neutral atoms. And neutral atoms do not scatter photons the way free electrons do. The fog lifted. Light was released to travel freely through space. That moment, called recombination, produced the oldest light we can detect today. The cosmic microwave background radiation, a faint thermal glow stretched by 13.8 billion years of cosmic expansion into microwave wavelengths. When satellites like the Planck spacecraft mapped this ancient light, they found it was remarkably uniform, almost the same temperature in every direction. 2.725 Kelvin, just a hair above absolute zero, but not perfectly uniform. Tiny variations existed. Fluctuations of perhaps 1 part in 100,000. Slightly warmer spots here, slightly cooler spots there. These minuscule temperature differences corresponded to minuscule density differences, regions where matter was packed just a fraction more tightly than average, regions where matter was spread just a fraction more thinly. Those tiny density differences were the seeds of everything. Every galaxy, every star, every planet, every atom in your body traces back to a region of the infant universe that was barely, almost imperceptibly, denser than its surroundings. But seeds do not become forests overnight, and in the universe after recombination, growth was agonizingly slow. The cosmos entered a period astronomers call the Dark Ages. No stars existed, no galaxies shone. The only light in the universe was the fading afterglow of the Big Bang itself, growing dimmer and cooler with every passing million years. Space was filled with neutral hydrogen and helium gas, invisible and featureless, slowly responding to the pull of gravity. Try to imagine what those dark ages were like. Not the darkness of a night sky peppered with stars, because no stars existed. Not the darkness of deep space between galaxies, because the gas was everywhere, filling every cubic meter of the cosmos with a thin, cold, invisible medium. This was a darkness more total and more uniform than anything in the modern universe. No point sources of light anywhere. No concentrated objects of any kind. Just an expanding ocean of neutral gas, featureless from horizon to horizon, across a cosmos that was already millions of light years wide, but contained nothing worth looking at. The temperature of this gas was dropping steadily as the universe expanded, falling from thousands of degrees to hundreds, then to tens, approaching the frigid baseline that would characterize most of intergalactic space for the rest of cosmic history. This era lasted for tens of millions of years. Some estimates stretch it to 100 million years or more before the first glimmers of starlight appeared. By the standards of human experience, that is an eternity. By the standards of cosmic evolution, it was the long, quiet pause between the fireworks of the Big Bang and the slow awakening of structure. Gravity is the architect of cosmic structure, but it is also the slowest architect imaginable. It works on timescales that make geological processes look frantic. In the Dark Ages, gravity began pulling gas toward the regions where matter was slightly denser. But the process was extraordinarily gradual. Gas does not simply fall inward like a rock dropping off a cliff. It resists compression. As gas contracts under gravity, it heats up. That heat creates pressure that pushes back against the collapse. The gas has to find a way to radiate that heat away before it can continue falling inward. In the early universe, with no heavy elements to act as efficient radiators, cooling was slow. Hydrogen and helium are terrible at shedding heat. Compared to heavier elements like carbon or oxygen, the gas could only cool through specific atomic transitions and molecular hydrogen formation, both of which operated at modest rates. This is why theorists expected the first galaxies to take their time. The raw materials were there, gravity was pulling, but the cooling process throttled the whole operation. Gas had to cool before it could collapse. It had to collapse before it could fragment. It had to fragment before individual clumps could reach the densities needed to ignite nuclear fusion. Every step in the chain imposed a delay, and every delay pushed the formation of the first luminous objects further into the future. There was another factor that made the slow timeline seem inevitable: dark matter. Cosmologists have known for decades that ordinary matter, the stuff that makes up stars and planets and human beings, accounts for only about 5% of the total energy content of the universe. Roughly 27% is dark matter, a substance that interacts with gravity but not with light. It does not emit photons. It does not absorb them. It does not scatter them. It is invisible to every telescope ever built, but its gravitational influence is enormous. Dark matter played a critical role in the theoretical picture of first galaxy formation. Because dark matter does not interact with radiation, it began clumping together earlier than ordinary matter did. While photons were still bouncing around in the hot plasma of the pre-recombination universe, preventing ordinary matter from collapsing, dark matter was already quietly assembling into structures. These structures are called halos. roughly spherical concentrations of dark matter that formed the gravitational scaffolding for everything that came after. The process was hierarchical. Small halos formed first, they merged into larger halos, those merged into still larger ones. Over hundreds of millions of years, this merging built halos massive enough to trap significant quantities of ordinary gas within their gravitational wells. When gas fell into these halos, it heated up from the gravitational energy of infall. Then, slowly, it cooled. Then, slowly, it collapsed to higher densities. Then, eventually, it formed stars. The theoretical framework predicted this process would produce the first tiny proto-galaxies somewhere around 100 to 200 million years after the Big Bang. But these were not galaxies in any sense a modern astronomer would recognize. They were small clumps containing maybe a few 100,000 solar masses of gas. Their first stars would have been unusual by today's standards. Formed from pure hydrogen and helium with no heavier elements to help the gas cool efficiently, these so-called population 3 stars were predicted to be enormous, possibly hundreds of times the mass of our Sun. Blazing hot, incredibly luminous individually but short-lived, burning through their fuel in just a few million years before exploding as supernovae. No one has ever observed a population 3 star directly. They are theoretical constructs predicted by models of how gas collapses and fragments in the absence of heavy elements. But the physics behind the prediction is straightforward. Without carbon, oxygen, and other heavy elements to radiate away heat efficiently, collapsing gas clouds in the early universe could not fragment into the small, dense cores that produce stars like our Sun. Instead, the gas remained warmer, the clouds stayed larger, and the resulting stars were massive. Some models predict individual population, 3 stars of 300 solar masses or more. Others suggest even larger objects, up to 1,000 solar masses, though these extreme predictions carry significant uncertainty. What is not uncertain is what happened when these stars died. A star of 200 solar masses does not fade quietly. It explodes with a violence that dwarfs ordinary supernovae. Some of these explosions, called pair instability supernovae, are predicted to be so energetic that they completely destroy the star, leaving no remnant behind, no neutron star, no black hole, just an expanding shell of process material blasting outward at thousands of kilometers per second. Other massive stars, depending on their exact mass and rotation, may collapse directly into black holes, potentially seeding the supermassive black holes that would later inhabit the centers of galaxies. Either way, these explosions were critical because they seeded the surrounding gas with the first heavy elements: carbon, oxygen, silicon, iron. For the first time, the universe contained the raw ingredients for rocky planets and complex chemistry. But the process was local and gradual. Each supernova enriched only a small volume of gas. The heavy elements did not spread uniformly across the cosmos. They remained concentrated near the sites of the explosions, mixing slowly into the surrounding hydrogen and helium through turbulence and gravitational stirring. A second generation of stars forming from this mildly enriched gas would have different properties. The presence of even trace amounts of carbon and oxygen dramatically improves a gas cloud's ability to radiate heat, allowing it to cool more quickly and fragment into smaller clumps. These second-generation stars would have been smaller, closer in mass to the stars we see in the modern universe. They would have lived longer. They would have produced their own complement of heavy elements and scattered them outward when they died, further enriching the surrounding medium. Building up a meaningful abundance of heavy elements across an entire galaxy took many generations of this cycle, each one living, dying, and scattering its enriched material into the surrounding medium. Stars form, stars live, stars die. Their ashes seed the next generation. The process is cumulative but slow. Each cycle takes millions of years for the most massive stars, and the enrichment is patchy, concentrated around the densest star-forming regions and diluted in the voids between them. This is why astronomers expected the first galaxies to be chemically primitive. If you are seeing a galaxy at a redshift of 12 or 13, corresponding to roughly 300 to 400 million years after the Big Bang, you are seeing a system that has had at most a few generations of stars. The heavy element content should be extremely low. The dust content, since dust is made from heavy elements, should be negligible. The overall structure should be irregular, because the galaxy has not had time to settle into an organized rotation pattern like a modern spiral. The simulations reinforce this picture with remarkable consistency. Research groups around the world use supercomputers to model the formation of the first cosmic structures. They fed in the known properties of dark matter, the measured density fluctuations from the cosmic microwave background, the established physics of gas cooling and star formation, and let the simulations run forward in time. The results converged on a consistent story. First light appeared somewhere around 100 to 250 million years after the Big Bang. The first galaxies were dim, they were small, they were far less luminous than modern galaxies by factors of thousands or more. Their stellar populations were tiny, their structures were irregular. They existed in modest numbers, scattered across space in the densest nodes of the emerging cosmic web. The numbers mattered enormously. Theoretical models predicted not just what individual galaxies should look like, but how many of them should exist at any given brightness level. This prediction is called the ultraviolet luminosity function. It describes how many galaxies you should find per unit volume of space at each level of brightness. Before Webb launched, the luminosity function at redshifts above 10 was thought to be steep and sparse, a few faint objects scattered across vast volumes of space. Finding even one galaxy at a redshift of 12 would have been a triumph. Finding a bright one would have been surprising. Finding many bright ones would have been inexplicable. This entire theoretical edifice rested on a deeper assumption that deserves careful attention. The standard model of cosmology, called lambda cold dark matter, had been tested against a staggering range of observations and passed every one. It explained the temperature fluctuations in the cosmic microwave background with extraordinary precision. It predicted the large-scale distribution of galaxies across the cosmic web. It accounted for the abundances of light elements produced in the first 3 minutes. It matched observations of distant supernovae that revealed the accelerating expansion of the universe. Lambda CDM was not a speculative framework. It was the most successful cosmological model ever constructed, validated across multiple independent lines of evidence spanning billions of years of cosmic history. Within this framework, galaxy formation was governed by well-understood physics. Gravity pulled matter together, gas cooled and collapsed, stars formed from the densest regions. Feedback from supernovae and radiation regulated the process, preventing gas from converting into stars too efficiently. The typical star formation efficiency, meaning the fraction of available gas that actually becomes stars in a given period, was estimated at roughly 1 to 3% in the early universe. This number came from both simulations and observations of galaxies at lower redshifts, and it was considered robust. 1 to 3%. That number will become very important later. There was one more piece of the prediction that mattered: reionization. After recombination filled the universe with neutral hydrogen, that hydrogen acted as a fog for certain wavelengths of light. Specifically, it absorbed ultraviolet radiation with energies high enough to ionize hydrogen atoms. This meant that the first galaxies were essentially shrouded. Their ultraviolet light could not travel far before being absorbed by the surrounding neutral medium. Only when enough stars had formed and produced enough ionizing radiation to carve out bubbles of ionized gas around them could their light begin to escape. This process, called reionization, was expected to unfold gradually over hundreds of millions of years. Early galaxies would ionize small bubbles around themselves. As more galaxies formed and more bubbles appeared, the bubbles would grow and eventually merge, clearing the cosmic fog entirely. Observations of distant quasars and the cosmic microwave background suggested that reionization was largely complete by about 1 billion years after the Big Bang. But at redshifts above 10, corresponding to less than 500 million years after the Big Bang, the universe was expected to be still deeply shrouded. Neutral hydrogen should have been thick and pervasive. Light from galaxies at these extreme distances should have been heavily absorbed, making the galaxies even harder to detect. This was the full prediction. Small galaxies, faint galaxies, chemically primitive galaxies, irregular galaxies, rare galaxies, shrouded in a fog of neutral hydrogen that blocked their most energetic light, forming stars at a modest efficiency of 1 to 3%, assembled from dark matter halos that had barely had time to merge into anything substantial. This was the cosmic dawn that decades of theory, simulation, and observation had prepared astronomers to find. And there was a very specific reason why nobody had been able to test this prediction directly before Webb. The light from these galaxies has been travelling for over 13 billion years. During that journey, the expansion of the universe has stretched the wavelength of every photon. Light that left these galaxies as ultraviolet radiation, the kind produced by hot young stars, has been stretched so severely that by the time it reaches Earth, it has shifted entirely out of the visible spectrum and deep into the infrared. Hubble could see some near-infrared light, but its mirror was too small and its infrared sensitivity too limited to detect the faintest, most distant galaxies at cosmic dawn. Hubble managed to find a handful of candidate galaxies at redshifts around 10 to 11, but these were right at the edge of its capability. Confirming their distances required spectroscopy, splitting the light into its component wavelengths to identify specific features, and Hubble simply did not have the infrared spectroscopic power to do this reliably at such extreme distances. Ground-based telescopes face their own barrier. Earth's atmosphere absorbs and emits infrared radiation, creating a blinding foreground glow that drowns out the faint signals from distant galaxies. Observing the first galaxies from the ground was like trying to see fireflies while standing inside a furnace. Everything pointed to the same conclusion. To see the first galaxies, to test the predictions that decades of theory had built, astronomy needed a telescope that was optimized for infrared observation, situated far from Earth's atmospheric interference, and equipped with a mirror large enough to collect the vanishingly faint light from objects at the edge of the observable universe. That telescope was the James Webb Space Telescope, 25 years in development, $10 billion in total cost. A 6.5-meter primary mirror made of 18 gold-coated hexagonal segments, 4 scientific instruments spanning near-infrared to mid-infrared wavelengths, launched on December 25, 2021, aboard an Ariane 5 rocket from French Guiana. Deployed to a point 1.5 million kilometers from Earth called the second Lagrange point, where it orbits the Sun in gravitational lockstep with our planet, permanently shielded from solar and terrestrial heat by a tennis court-sized sunshield. Webb was designed, from its inception, to answer the question of when and how the first galaxies formed. Its instruments were built to detect infrared light from the most distant objects in the universe. Its spectrograph, called near-spec, could split that light into its component wavelengths to determine precise distances, chemical compositions, and physical properties. Its primary camera, NIR-CAM, could take deep images across multiple infrared filters, allowing astronomers to estimate distances even before spectroscopic confirmation. The telescope arrived at its destination in January 2022. It spent the next 6 months unfolding, cooling, aligning its mirrors, and calibrating its instruments. By July 2022, it was ready to observe. The scientific community held its collective breath. The predictions were in place. The models were published. The luminosity functions were plotted. The expected number counts were calculated. Everyone knew what the first galaxies should look like, and then Webb opened its eyes. The very first deep field image, released on July 11th, 2022, covered a patch of sky roughly the size of a grain of sand, held at arm's length by someone standing on the ground. Within that absurdly small sliver of sky, Webb revealed thousands of galaxies stretching back across billions of years of cosmic time. Many of them were expected. Galaxies at moderate distances that Hubble had already catalogued in less detail. But scattered among them, glowing red with the telltale signature of extreme redshift, were objects that made astronomers pause. They were bright, too bright. They were numerous, too numerous. Some of them appeared structured and developed in ways that should have required far more time than the universe had provided. Within weeks of the first data release, research teams around the world began publishing results. Each paper carried the same undertone of cautious disbelief. The galaxies at the highest redshifts were not matching the predictions. They were not matching them badly, and the discrepancy was not subtle. The theoretical picture that had taken 30 years to build was about to collide with reality. What Webb found at cosmic dawn was not huts. It was something far more unsettling. The first clue arrived in a data format that most people would find profoundly underwhelming. Not a photograph, not a sweeping panorama of cosmic splendor. A graph. A plot of brightness versus wavelength for a tiny red smudge barely distinguishable from detector noise in a deep infrared image. But when astronomers on the JADES team saw that graph in late 2022, several of them stopped what they were doing and stared. The smudge was bright, far brighter than it had any right to be. And the pattern of its light, rising sharply at a specific wavelength and vanishing completely below it, pointed to a distance that seemed almost absurd. This object appeared to exist when the universe was less than 400 million years old. The feature they were seeing is called a Lyman break. It works like this. Hydrogen gas in the space between galaxies absorbs ultraviolet light at a very specific wavelength, 1,216 angstroms. For a nearby galaxy, this absorption happens in the ultraviolet part of the spectrum, far below what the human eye can see. But for a galaxy at extreme distance, the expansion of the universe has stretched all of its light toward longer wavelengths. The further away the galaxy, the more the stretching. At a redshift of 10, that absorption feature has been pushed from the ultraviolet all the way into the near-infrared, around 1.3 microns. At a redshift of 13, it sits near 1.7 microns. At a redshift of 14, past 1.8 microns. When astronomers take images of a distant galaxy through multiple infrared filters, the galaxy appears in the longer wavelength filters but vanishes completely in the shorter wavelength ones. That sharp cutoff is the Lyman break, and its position tells you how far away the galaxy is. The technique is not new. Hubble used it for years, but Webb's infrared sensitivity and mirror size made it devastatingly effective at distances Hubble could never reach. In those first months of data, the JADES survey, short for JWST Advanced Deep Extragalactic Survey, began identifying candidate galaxies at redshifts above 10, then above 11, then above 12. The candidates piled up. Some were faint, as expected, but others were not faint at all. They were blazing with ultraviolet luminosity that the models had not predicted. And there were more of them than anyone anticipated. Not a handful of rare outliers scattered across the survey field. Dozens. Eventually hundreds, as other survey programs like SEERS, GLASS and Uncover added their own data. The first spectroscopic confirmations arrived quickly. Spectroscopy is the gold standard in astronomy. Imaging can estimate a galaxy's distance using the Lyman break technique, but those estimates carry uncertainty. A galaxy that looks like it sits at redshift 12 based on its colours might actually be a dusty galaxy at redshift 3 mimicking the same colour pattern. Only spectroscopy, which spreads the galaxy's light into a detailed spectrum revealing emission and absorption lines at precise wavelengths, can nail the distance definitively. Webb's near-spec instrument was built for exactly this purpose. It carries a microshutter array, a grid of tiny configurable slits that can be opened individually to capture spectra from multiple galaxies simultaneously. The JADES team pointed NIRSpec at their highest priority candidates and collected data for staggering durations: 28 hours on a single field, 75 hours on another. These were among the longest spectroscopic exposures ever taken by any space telescope, and when the spectra came back, the candidates held up. In early 2023, the team published confirmations of 4 galaxies at redshifts between 10.4 and 13.2. The most distant, designated Jade's GSZ 13.0, existed when the universe was roughly 330 million years old. Its spectrum showed a clean Lyman break and faint ultraviolet continuum emission from young stars. It was real, it was far, and it was brighter than the models said it should be. But that was only the beginning. In 2024, the JADES team announced something that sent a shockwave through the astronomical community. The story of how that discovery unfolded reveals just how painstaking the process of confirming the most distant objects in the universe actually is. The galaxy that would become known as JADES GSZ 14.0 had first appeared as a candidate in earlier JADES imaging. But there was a problem. On the sky, it sat close enough to a foreground galaxy that the two objects could not be clearly separated. Were they neighbours at the same distance, or was the faint red smudge a vastly more distant background object whose light happened to fall along nearly the same line of sight? The team could not be sure. To resolve the ambiguity, the JADES collaboration conducted one of the most ambitious observations of their entire program. In October 2023, they dedicated 5 full days of Webb's time to a single field using NIRCam, creating what they called the JADES Origins field. The imaging used carefully chosen filters designed to better isolate galaxies at extreme redshifts from foreground contamination. As the data accumulated, confidence grew. The candidates' colours were consistent with a galaxy at a redshift of roughly 14. It was not blending with the foreground object. It was behind it, vastly more distant. Its light shifted deep into the infrared by over 13 billion years of cosmic expansion. But colours alone could not settle the question definitively. The team needed a spectrum, and so JADES GSZ 14.0 was included in what was planned as the capstone observation of the entire JADES program. A 75-hour spectroscopic campaign targeting the faintest, most distant galaxy candidates in their survey. 75 hours is an extraordinary investment of Webb's time. The telescope is in constant demand from research teams around the world, and every hour of observation must be justified. Committing 75 hours to a single spectroscopic pointing reflects the scientific stakes involved. This was the frontier. These were the most distant objects humans had ever attempted to characterize. When the spectrum of JADES GSZ 14.0 was first processed, the team saw what they had hoped for but had not dared to assume. A clear Lyman break at a wavelength consistent with a redshift of 14.32. An ultraviolet continuum from young stars extending to longer wavelengths. No ambiguity, no alternative explanation. This galaxy existed just 290 million years after the Big Bang. It was the most distant spectroscopically confirmed galaxy ever observed. What made JADES GS 14.0 remarkable was not just its distance, it was its luminosity. The galaxy was bright enough that Webb could have detected it, even if it were 10 times fainter. That meant it was not some marginal detection hovering at the edge of the telescope's capability. It was a robust, confident measurement of an object that had no business being that luminous at that distance. Its light was powered predominantly by stars, not by an accreting black hole. Analysis of its spectrum showed evidence of a stellar continuum with hints of dust reddening, meaning the galaxy had already formed enough heavy elements and processed enough material to produce dust grains. At less than 300 million years old, this galaxy was not a primordial wisp. It was a functioning stellar system with chemical complexity. The discovery paper laid it out plainly. The existence of this galaxy, and the rate at which similarly luminous objects were turning up across the survey, had profound implications for the predicted number of bright galaxies in the early universe. The researchers concluded that luminous galaxies were far more common at cosmic dawn than any pre-Webb model had anticipated. Then, in 2025, the record fell again. A galaxy designated MOM Z14, discovered by the Mirage or Miracle Spectroscopic Survey, was confirmed at a redshift of 14.44. This pushed the observational frontier to just 280 million years after the Big Bang. According to NASA, MOM Z14 was brighter, more compact, and more chemically enriched than astronomers anticipated for such an early era. It showed elevated levels of nitrogen, a finding that suggested massive stars had already formed, evolved, fused heavier elements in their cores, and expelled those elements into the surrounding gas. The galaxy also appeared to have cleared its surrounding region of primordial hydrogen gas, an unexpected finding given how young it was. The lead researcher on the discovery noted that roughly 100 or more relatively bright galaxies now existed in the JWST data at redshifts between 14 and 15, a range where pre-Webb consensus expected to find almost none. The telescope had not been designed to find galaxies this luminous this early. It found them anyway. Meanwhile, another discovery was unfolding that complicated the picture even further. In March 2025, a team studying one of the most distant known galaxies announced a finding that challenged the established understanding of how light escapes from the early universe. The galaxy Jade's GSZ 13.1, confirmed at a redshift of 13.05, corresponding to roughly 330 million years after the Big Bang, showed strong Lyman alpha emission in its spectrum. This was not supposed to happen. Lyman alpha emission is produced when hydrogen atoms in a galaxy are ionized by starlight and then recombine, emitting a photon at a characteristic wavelength. It is one of the most common spectral signatures of star-forming galaxies, but at redshift 13, the universe was still deep in the epoch of reionization. Neutral hydrogen gas filled the space between galaxies like a dense fog. That fog is extremely effective at absorbing Lyman alpha photons. Even a small column of neutral hydrogen can block the signal entirely. For a galaxy at this distance to show bright Lyman alpha emission, something had to have cleared a path. Either the galaxy had ionized a substantial bubble in the surrounding neutral medium far earlier than expected, or some other mechanism was punching through the fog. One researcher on the team described it in striking terms. The early universe should have been shrouded in a thick fog that would make it exceedingly difficult to find even powerful lighthouses peeking through. Yet here was a beam of light from this galaxy piercing the veil. The findings suggested that at least some galaxies at cosmic dawn were more powerful, more energetic, and more capable of reshaping their environments than the standard picture allowed. These individual discoveries were dramatic enough, but the larger pattern emerging from the data was arguably more significant than any single galaxy. Across multiple independent surveys using different fields and different analysis techniques, the same conclusion kept appearing. The ultraviolet luminosity function at redshifts above 9 or 10 was significantly higher than predicted. There were more bright galaxies per unit volume of space than the models had forecast, not slightly more, in some redshift bins, an order of magnitude more. To grasp what that means, consider the prediction in concrete terms. Before Webb, if you pointed a theoretical telescope at a volume of space 1 billion cubic light-years in size at a redshift of 12, the models told you to expect perhaps 1 or 2 galaxies brighter than a certain threshold, maybe 3 in a generous estimate. Webb found 10, or 20, or more. In the highest redshift bins, at redshifts of 13 and 14, the models predicted you might find 0 bright galaxies in a typical survey volume. Webb found dozens. The discrepancy was not a subtle statistical wobble. It was as if you walked into a desert expecting to find 1 or 2 puddles and instead found a lake. The individual puddles might have reasonable explanations. The lake demands a fundamentally different story about where the water came from. The discrepancy was largest at the highest redshifts, exactly where the predictions had been most confident that bright galaxies should be exceedingly rare. The early papers framed this carefully. Photometric candidate galaxies, those identified by their colours but not yet confirmed spectroscopically, carried inherent uncertainty. Some fraction of them might turn out to be lower redshift interlopers, dusty galaxies or brown dwarfs masquerading as high redshift objects. But as the spectroscopic confirmations accumulated, the contamination rate turned out to be surprisingly low. Study after study found that the photometric selections were largely reliable. The bright galaxies were real, they were distant, and there were too many of them. Then came the little red dots. Among the thousands of objects Webb detected in its deep surveys, a strange population began to emerge. Small, compact, intensely red at longer infrared wavelengths but blue at shorter wavelengths. They had never been seen before. Hubble could not have detected them. They existed primarily between 600 million and 1.6 billion years after the Big Bang, with the majority concentrated around 600 million years. By 2025, over 340 of these objects had been identified in JWST data across multiple survey fields. The little red dots, as they were quickly nicknamed, created immediate confusion. When astronomers estimated their properties using standard techniques, treating them as normal galaxies and fitting their observed light to models of stellar populations, the numbers came back impossibly large. These tiny objects appeared to contain as many stars as the Milky Way. Their implied masses were so enormous that they could not have assembled in the time available since the Big Bang. Headlines erupted. Universe-breaking galaxies. Cosmology in crisis. The standard model is wrong. But the scientific community urged caution. Something about the little red dots did not add up. Their spectra showed broad emission lines, a hallmark of gas moving at extreme velocities near a massive object. In modern galaxies, broad emission lines are the signature of active galactic nuclei, supermassive black holes at galaxy centers devouring material from an accretion disk. The friction in that infalling gas produces enormous amounts of light and heat. But the little red dots did not match known active galactic nuclei cleanly. They lacked the expected X-ray emission. They lacked the expected radio emission. They were red in ways that did not correspond neatly to either dusty galaxies or typical quasars. A fierce scientific debate erupted. One camp argued the little red dots were genuinely massive galaxies packed with stars and dust. If true, this would pose a severe challenge to the standard cosmological model, because there simply was not enough time or material available to build galaxies that large that early. The other camp argued they were compact objects powered by accreting black holes, and that the extreme brightness was coming from the black hole's accretion disk, not from an impossibly large stellar population. In this interpretation, the galaxies were not actually massive. They just appeared massive because the black hole was contributing an enormous amount of extra light. The debate has not fully resolved, but by late 2025, the evidence had shifted significantly toward the black hole interpretation. A major study from the University of Texas at Austin, published in the Astronomical Journal, systematically examined a sample of early galaxies from the Sears survey. The researchers identified which objects in the sample were little red dots and removed them from the analysis. When they did this, the remaining galaxies, the ones that appeared to be genuine star-forming systems rather than black hole-powered objects, were not too massive to fit within the standard model. The crisis-level tension disappeared. As one of the lead researchers put it, there is no crisis in terms of the standard model of cosmology. The little red dots had been inflating the apparent mass estimates and creating a false signal of impossibly massive galaxies. Remove them, and the remaining population is surprising but not cosmology-breaking. But that was not the end of the story. Even with the little red dots excluded, there were still roughly twice as many massive galaxies in the early universe as pre-Webb models predicted. The tension was reduced from crisis to puzzle, but the puzzle remained real. Something about galaxy formation in the early universe was more efficient, more rapid, or more productive than the models had captured. The nature of the little red dots themselves remained an open and rapidly evolving question. In 2025 and into 2026, competing theories proliferated. A study published in Nature in January 2026 analysed the highest quality JWST spectra of little red dots and concluded that in most cases, The broad emission lines were being broadened not by the high-velocity orbital motion of gas around a black hole, as traditionally assumed, but by electrons scattering in an extremely dense cocoon of ionized gas surrounding a young supermassive black hole. This implied that the black holes at the centers of little red dots were significantly less massive than initial estimates suggested, perhaps 100 to 1,000 times less massive, but were accreting material at extraordinary rates while shrouded in thick envelopes of gas. Other researchers proposed even more exotic possibilities. A study from mid-2025 suggested that some little red dots might not be galaxies or conventional black holes at all, but rather supermassive primordial stars. Population 3 behemoths of perhaps 1 million solar masses observed in the final few thousand years of their lifetimes. The theoretical spectra of such objects match the observed features of little red dots remarkably well, including a distinctive V-shaped break in the spectrum called the Balmer break. If correct, this interpretation would mean that some little red dots are direct windows into the formation of the very first supermassive black holes, the progenitors of the monsters that sit at the centers of nearly every large galaxy today. A Harvard-Smithsonian team offered yet another explanation, proposing that little red dots formed in dark matter halos with unusually low spin. Most dark matter halos rotate, and that rotation spreads out the gas within them, producing extended galaxies. But halos in the lowest 1% of the spin distribution would keep their gas extremely concentrated, producing the ultra-compact, intensely luminous objects that JWST observed. This model naturally explains several puzzling features: why little red dots are rare, why they appear only during a specific window of cosmic time, and why they disappear at later epochs when halos have gained more angular momentum through mergers. Each of these interpretations carries different implications for our understanding of the early universe. If little red dots are conventional active galactic nuclei, they tell us that supermassive black holes formed and began accreting material far earlier than expected. If they are electron-scattering shrouded black holes, they tell us that early black hole growth may have proceeded through dense, cocooned phases, invisible to most wavelengths. If they are supermassive primordial stars, they tell us that the first generation of stars included objects so extreme that nothing like them exists in the modern universe. And if they are low-spin halo products, they tell us that the statistical distribution of dark matter properties played a more important role in early galaxy formation than anyone had appreciated. As of early 2026, no single explanation has won the debate. The community has converged on the broad conclusion that little red dots involve supermassive black holes in some form, but the details remain fiercely contested. What is clear is that they represent a population of objects that was entirely invisible before Webb, and that has no obvious counterpart in the nearby universe. Beyond the individual record-breaking galaxies and the mystery of the little red dots, Webb's surveys revealed a broader pattern of structural and chemical maturity at cosmic dawn that defied expectations. Some early galaxies showed spiral structures, organized rotation patterns that were thought to require billions of years of gravitational settling to develop. A galaxy nicknamed the Big Wheel, discovered in early 2025, exhibited clear spiral arms despite existing within the first 2 billion years of cosmic history. Its size and structure resembled galaxies that are far more common in the modern universe, raising the question of how gravitational dynamics could produce such order so quickly. Other early galaxies showed chemical signatures that suggested rapid and efficient enrichment. Elevated nitrogen abundances in MOMSI 14 implied that massive stars had already cycled through their entire lifetimes, fusing hydrogen into helium, helium into carbon, carbon into nitrogen through specific nuclear processes, and expelling those products into the galaxy's gas reservoir. This chain of events normally takes tens of millions of years per stellar generation, and multiple generations appeared to have already occurred within the first 300 million years. Dust was another surprise. Dust grains form from heavy elements, which means they can only exist after stars have lived and died and scattered their processed material into space. Finding dust in galaxies at redshifts above 10 indicated that at least some systems had already completed multiple cycles of star formation and stellar death. The universe was not chemically primitive at 300 million years, it was already cooking. A comprehensive perspective paper published in Nature Astronomy in August 2025, synthesizing the insights of an international assembly of leading astronomers, captured the state of knowledge. JWST had revealed that galaxies and black holes formed far earlier than expected, rapidly building up stellar mass, dust, and heavy elements within just a few 100 million years. The telescope had uncovered a surprising abundance of massive, luminous galaxies and compact star clusters at cosmic dawn, challenging existing models of galaxy formation. Thousands of galaxies from the epoch of reionization had now been identified, with individual ionized bubbles traced back to specific star-forming galaxies. The authors described this as a transformative moment in cosmic research, one that was rewriting our understanding of cosmic origins. The observations were not ambiguous. They were not marginal detections subject to interpretation. They were confirmed, spectroscopic, multi-wavelength measurements of real objects at real distances, obtained by the most powerful infrared telescope ever built, and analysed by independent teams using independent methods. The early universe was brighter than predicted. It was more chemically evolved than predicted. It was more structurally mature than predicted. And it contained more galaxies and more active black holes than predicted. None of this meant that the Big Bang was wrong. None of it meant that the age of the universe needed to be revised. None of it meant that cosmology had collapsed. But it did mean that something in the machinery of galaxy formation, the physics connecting dark matter halos to gas cooling, to star formation, to chemical enrichment, was operating differently in the early universe than theorists had assumed. The question was no longer whether the predictions were wrong. The question was why. When the first JWST results hit the preprint servers in mid-2022, the headlines wrote themselves: Impossible Galaxies, Universe-Breaking Discoveries, Scientists Baffled, The Standard Model in Ruins. Social media amplified the most dramatic interpretations. Some commentators declared that the Big Bang had been disproven. Others claimed that the age of the universe was wrong, that cosmology had been lying to us for decades, that everything we thought we knew about the cosmos was collapsing under the weight of Webb's observations. None of this was true, but the temptation to leap from surprising data to revolutionary conclusions proved nearly irresistible in the public sphere, and even some professional astronomers published papers with titles that flirted with catastrophe. The reality, as it usually does in science, turned out to be more nuanced and ultimately more interesting than the panic suggested. The bright early galaxies were real. The tension with pre-Webb models was genuine. But the path from tension to explanation did not require throwing out modern cosmology. It required understanding where the models had gone wrong and why. And that understanding arrived in stages, each one peeling back a different layer of assumption that had made the predictions too conservative. The first layer was the most mundane and the easiest to fix: calibration. When Webb began taking data, its instruments were still being fine-tuned. The detectors that measure incoming infrared light needed precise calibration to convert raw pixel counts into accurate brightness measurements. In the first months of operation, those calibrations carried meaningful uncertainty. If the brightness of a distant galaxy was overestimated by even a modest amount, the galaxy would appear more luminous than it actually was. Multiply that error across hundreds of galaxies in a statistical sample, and the luminosity function at high redshift would appear inflated. Astronomers recognized this immediately and began refining the calibrations using observations of known reference objects. As the calibration improved through late 2022 and into 2023, some of the most extreme brightness estimates were revised downward. A few candidate galaxies that had appeared spectacularly luminous turned out to be slightly less dramatic than the initial measurements suggested. This did not eliminate the tension, but it shaved off a piece of it, bringing the most extreme outliers somewhat closer to the theoretical predictions. The second layer involved a more fundamental issue: mistaken identity. As we have seen, a significant fraction of the objects that initially appeared to be impossibly massive galaxies turned out to be little red dots. Compact objects whose extraordinary brightness was driven not by enormous stellar populations but by actively accreting black holes. When astronomers treated these objects as normal galaxies and estimated their stellar masses from their total brightness, the numbers came back absurdly high. But the brightness was not coming from stars. It was coming from the intense radiation of gas spiraling into a central black hole at tremendous speeds. The black hole's accretion disk acted like a cosmic spotlight, making the galaxy appear far more massive than it actually was. The critical study that clarified this point came from a team led by a graduate student at the University of Texas at Austin, working within the Sears Survey collaboration. The researchers systematically identified which galaxies in their early universe sample were little red dots and separated them from the rest of the population. When the little red dots were removed, the remaining galaxies fit much more comfortably within the predictions of the standard cosmological model. The masses were still high, but they were no longer impossible. The apparent crisis dissolved. This was an important moment in the story. It demonstrated that the most alarming interpretation of Webb's data, the claim that early galaxies were so massive they broke cosmology, had been driven partly by a population of objects that were not conventional galaxies at all. The little red dots had contaminated the sample, inflating the mass estimates and creating a false signal of cosmological catastrophe. Once they were properly accounted for, the standard model of cosmology survived intact. But this did not mean everything was fine. The same study that removed the crisis also confirmed that a real, if less dramatic, puzzle remained. Even after excluding the little red dots, there were still roughly twice as many massive galaxies at cosmic dawn as the standard models predicted. This was not a universe-breaking discrepancy. It was a factor of 2, not a factor of 10. But a factor of 2 is not noise. It is a genuine signal that something in the physics of early galaxy formation was more productive than the models had assumed. Understanding that something required looking more carefully at the assumptions built into the theoretical predictions. And this is where the story becomes scientifically rich, because the explanations that emerged did not point to a single missing ingredient. They pointed to several, each addressing a different aspect of how galaxies convert gas into stars and light. The third layer of explanation focused on how stars form in the early universe. For decades, galaxy formation models had assumed that star formation proceeds at a roughly steady rate in most galaxies. Gas cools, collapses, forms stars, and does so continuously at a pace regulated by feedback from supernovae and radiation pressure. This assumption was not arbitrary. It was based on observations of galaxies in the nearby universe, where star formation rates are relatively stable over timescales of hundreds of millions of years. The models extrapolated this behavior backward in time, assuming that early galaxies followed similar patterns. But a team of astrophysicists led by researchers at Northwestern University and the Flatiron Institute's Center for Computational Astrophysics challenged this assumption using a suite of sophisticated simulations called FIRE, which stands for Feedback in Realistic Environments. When they ran their simulations to model galaxies forming at cosmic dawn, they found that star formation did not proceed steadily. It proceeded in violent, irregular bursts. The physics behind this is intuitive once you understand it. In a small young galaxy with a shallow gravitational well, star formation is a volatile process. Gas collapses and forms a cluster of stars. Those stars include massive, short-lived giants that burn through their nuclear fuel in just a few million years and explode as supernovae. The energy from those explosions blows gas out of the galaxy, temporarily shutting down star formation. But the gas does not escape permanently. Gravity pulls it back. It falls inward again, collapses again, and triggers another burst. The cycle repeats. Star formation happens in intense flashes separated by periods of relative quiescence. This pattern has a critical observational consequence. During a burst, a galaxy is temporarily much brighter than its average luminosity because it is producing massive, hot, luminous stars at an elevated rate. If you happen to observe the galaxy during one of these bursts, it looks far more impressive than its long-term average would suggest. It is like photographing a firefly at the exact moment it flashes. The photograph suggests a much brighter insect than the firefly actually is. Over the course of its entire blinking cycle, the fire simulations showed that this bursty star formation could naturally explain why JWST was seeing so many bright galaxies at cosmic dawn. The galaxies were not necessarily more massive than predicted. They were being caught during their brightest moments. The statistical effect is amplified by a phenomenon called Eddington bias. Because there are far more faint galaxies than bright ones at any given time, even a modest amount of brightness variability will scatter some faint galaxies above the detection threshold, making the bright end of the luminosity function appear more populated than it would if star formation were steady. The simulations matched the observed luminosity functions remarkably well. The number of bright galaxies predicted by the bursty models agreed with the number JWST actually found. And crucially, the simulations achieved this agreement without invoking any exotic new physics. They used the same cosmological framework, the same dark matter properties, the same gas physics. The only difference was allowing star formation to be realistically variable rather than artificially smooth. This was a significant result because it suggested that the pre-Webb predictions had been too conservative, not because of a flaw in fundamental cosmology, but because of an oversimplification in how star formation was modelled. The standard model of the universe was fine. The standard model of star formation needed updating. But bursty star formation alone could not explain everything. Even accounting for brightness fluctuations, some early galaxies appeared to have formed more total stellar mass than the models predicted. This pointed to a fourth layer of explanation. The efficiency of star formation itself might have been higher in the early universe. In the local universe, the fraction of available gas that converts into stars over a given period is remarkably low, roughly 1 to 3%. The rest of the gas remains unconverted, held at bay by various feedback mechanisms. Supernovae inject energy into the surrounding gas, heating it and preventing it from collapsing. Radiation from massive stars ionizes and pushes away nearby material. Turbulence stirs the gas, supporting it against gravitational collapse. These processes are collectively called stellar feedback, and they are extraordinarily effective at regulating star formation. Without feedback, simulations show that gas in galaxies would convert into stars far too quickly, producing galaxies much more massive and luminous than anything we observe. But the effectiveness of feedback depends on the environment, and the environment at cosmic dawn was fundamentally different from the local universe. The key difference is density. The universe at a redshift of 10 was roughly 1,000 times denser on average than it is today. Dark matter halos at cosmic dawn were more compact. The gas within them was denser and more concentrated. In this denser environment, supernova-driven outflows had a harder time escaping. The deeper gravitational wells trapped more of the expelled gas, which then fell back and fueled further star formation more quickly. Several research groups explored this idea using both analytical models and simulations. They found that at the gas surface densities expected in massive early galaxies, star formation efficiency could plausibly increase to 5, 10, or even 20%, far above the 1 to 3% typical of the local universe. This higher efficiency would naturally produce more stellar mass in a given amount of time, explaining why some early galaxies appeared more massive and luminous than models based on local efficiency values had predicted. This explanation did not require changing the laws of physics. It required recognizing that the physical conditions in the early universe, specifically the higher gas densities and deeper gravitational wells, created an environment where the same physics operated differently. Supernovae still exploded, radiation still pushed on gas, turbulence still stirred, but the balance between gravity and feedback shifted in favor of gravity, allowing gas to form stars more readily. Some researchers pushed this idea further, suggesting that the initial mass function of stars, the distribution of stellar masses at birth, might also have been different at cosmic dawn. If early galaxies produce proportionally more massive stars than local galaxies do, those massive stars would have been disproportionately luminous, making the galaxy brighter for a given total stellar mass. This would compound the effect of higher star formation efficiency, making early galaxies appear even more impressive than their mass alone would suggest. The evidence for a modified initial mass function is still debated. Some spectroscopic observations of early galaxies show signatures consistent with a top-heavy stellar population, meaning more massive stars relative to low-mass ones. Others show no clear deviation from the standard distribution. The question remains open, but it represents another mechanism that could contribute to the unexpectedly bright early galaxies without requiring any changes to fundamental cosmology. A fifth layer of explanation emerged from the mystery of Jade's GSZ 13.1, the galaxy at redshift 13 that displayed bright Lyman alpha emission through what should have been an opaque wall of neutral hydrogen. Multiple hypotheses were proposed to explain how this galaxy's ultraviolet light escaped the cosmic fog. One possibility is that the galaxy carved an ionized bubble in the surrounding neutral medium much earlier than expected. If a galaxy produces enough ionizing photons, it can strip electrons from the hydrogen atoms in its immediate vicinity, creating a transparent region through which Lyman alpha photons can travel freely. For this to work at redshift 13, the galaxy would need to have been forming stars vigorously for tens of millions of years already, producing a sustained output of ultraviolet radiation sufficient to ionize a significant volume of surrounding gas. This scenario is consistent with the idea that some early galaxies were more powerful and more productive than models assumed. Another possibility involves the geometry of reionization itself. If the universe's transition from neutral to ionized was not smooth and uniform but instead patchy, proceeding unevenly with some regions ionizing earlier than others, then a galaxy sitting inside an early ionized patch could show Lyman alpha emission, even though the universe as a whole was still mostly neutral. This is not a new idea. Theorists have long expected reionization to be inhomogeneous, but the detection of Lyman alpha at redshift 13 suggests the patchiness may have begun earlier and been more extreme than previously modelled. A third possibility, raised by the discovery team itself, is that the galaxy hosts an active galactic nucleus, whose intense radiation output helps ionize the surrounding gas more efficiently than stars alone could. If a young supermassive black hole at the center of Jade's GSZ 13.1 was accreting material and producing copious ultraviolet and X-ray photons, it could have cleared a path through the neutral hydrogen more quickly than stellar radiation alone. Each of these explanations carries different implications for the broader picture of reionization. If early galaxies routinely carved ionized bubbles ahead of the expected timeline, it means the process of cosmic reionization began earlier and progressed faster than current models assume. This would require either more galaxies, brighter galaxies, or galaxies with higher escape fractions of ionizing radiation at very high redshifts. All three possibilities are consistent with the general pattern of Webb's findings. The early universe was more active, more luminous, and more capable of reshaping its own environment than the theoretical consensus had anticipated. Taken together, these explanations form a coherent narrative, though not yet a complete one. The initial alarm over impossible galaxies was partly a measurement artifact, driven by instrument calibration issues and the contamination of galaxy samples by little red dots whose brightness came from black holes rather than stellar mass. Once these factors were accounted for, the standard model of cosmology remained intact. No exotic new physics was required. The Big Bang did not need to be revised. The age of the universe did not need to change. But a genuine and scientifically productive tension remained. The early universe formed galaxies faster, brighter, and more efficiently than models had predicted. The leading explanations involve bursty star formation that creates temporary flashes of brightness, higher star formation efficiency driven by the denser conditions at cosmic dawn, and the presence of actively accreting black holes that boost the luminosity of compact early galaxies. None of these explanations are mutually exclusive. The real answer almost certainly involves some combination of all of them, operating simultaneously in different galaxies and at different epochs. The scientific community has reached a provisional consensus that can be summarized in a single sentence. The standard model of cosmology is not broken, but the standard models of galaxy formation need significant revision to accommodate the complexity revealed by Webb. This is not a crisis, it is a correction. And in science, corrections are how progress happens. There is an important distinction here that deserves emphasis, because it is often lost in popular coverage of these discoveries. Cosmology and galaxy formation physics are related but different fields. Cosmology describes the large-scale properties of the universe, its geometry, its expansion rate, its total energy content, the nature of dark matter and dark energy. Galaxy formation physics describes the smaller-scale processes by which gas cools, collapses, forms stars, and assembles into the structures we recognize as galaxies. The standard model of cosmology, lambda CDM, governs the first set of questions. Galaxy formation models, which are built on top of lambda CDM but incorporate additional astrophysical assumptions about star formation, feedback, and gas dynamics, govern the second. Tom, what Webb challenged was not lambda CDM, it was the galaxy formation models built on top of it. The fundamental cosmological framework, the expansion history, the dark matter content, the primordial density fluctuations, all remain consistent with observations. What needed updating was the set of assumptions about how efficiently gas turns into stars in the early universe, how variable that process is over time, and how much light comes from black hole accretion versus stellar emission in the most distant objects. This distinction matters because it determines whether the response to Webb's discoveries is revolutionary or evolutionary. If lambda CDM itself were broken, that would be revolutionary. It would require rethinking the fundamental properties of the universe. But if the galaxy formation models need revision, that is evolutionary. It means refining our understanding of astrophysical processes within a cosmological framework that continues to work. The current state of knowledge is firmly in the evolutionary category. The adjustments needed to reconcile Webb's observations with theory are significant but not radical. Higher star formation efficiency at early times is physically motivated by the higher gas densities present in the young universe. Bursty star formation is a natural consequence of stellar feedback in small galaxies with shallow gravitational wells. Active black holes in compact early galaxies are consistent with the growing body of evidence that supermassive black holes formed earlier and grew faster than previously thought. What remains genuinely uncertain is the relative importance of each mechanism. How much of the brightness excess is explained by bursty star formation versus higher intrinsic efficiency? What fraction of the early galaxy population hosts active black holes? How common are the extreme objects like Jade's GSZ 14-0 relative to the broader population of fainter, more typical early galaxies? These questions require more data, more spectroscopic confirmations, and more sophisticated modeling to resolve. The conversation has also shifted toward understanding the connection between early galaxies and the supermassive black holes that inhabit them. One of Webb's most unexpected findings is that supermassive black holes appear to have formed and begun growing much earlier than any pre-Webb model anticipated. Galaxies that are only a few 100 million years old show evidence of central black holes with masses of millions of solar masses. In the local universe, supermassive black holes and their host galaxies appear to grow in tandem, maintaining a roughly proportional relationship between black hole mass and galaxy mass. But at cosmic dawn, the black holes seem to be ahead. They are overmassive relative to their host galaxies, as if the black hole started growing first and the galaxy is still catching up. To appreciate why this is so puzzling, you need to understand the physical constraint that governs how fast a black hole can grow. When a black hole accretes material, the infalling gas heats up to extreme temperatures and radiates intensely. That radiation exerts an outward pressure on the surrounding gas, pushing it away from the black hole. At a certain accretion rate, the outward radiation pressure exactly balances the inward gravitational pull. This balance point is called the Eddington limit, and it sets a maximum rate at which a black hole can consume material under normal circumstances. Feed a black hole faster than the Eddington rate, and the radiation blows the food supply away. The black hole effectively chokes on its own energy output. The Eddington limit creates a speed limit for black hole growth. A black hole accreting at the maximum allowed rate doubles its mass in roughly 50 million years. Starting from a stellar mass seed of perhaps 10 to 100 solar masses, the kind of black hole left behind by the death of a massive star, you can calculate how many doublings are needed to reach 1 million solar masses. The answer is roughly 13 to 17 doublings. At 50 million years per doubling, that requires somewhere between 650 million and 850 million years of continuous, maximal accretion with no interruptions, no periods of starvation, no events that slow the feeding. But Webb is finding black holes of 1 million solar masses or more in galaxies that are less than 400 million years old. The math does not work. Even accreting at the theoretical maximum from the moment the universe began, a stellar mass seed cannot grow large enough fast enough. This timeline problem has driven theorists to propose alternative pathways for forming much more massive black hole seeds directly, bypassing the slow growth from stellar remnants entirely. One leading idea involves direct collapse black holes. In this scenario, a massive cloud of primordial gas in the early universe, perhaps 100,000 solar masses worth, collapses directly into a black hole without first fragmenting into stars. For this to happen, the gas must be prevented from cooling efficiently, which requires specific conditions. The cloud must be bathed in a strong ultraviolet radiation field from a nearby galaxy, which destroys the molecular hydrogen that would otherwise allow the gas to cool, fragment, and form stars instead. If the cooling is suppressed, the entire cloud can collapse monolithically into a single massive object. The resulting black hole seed, starting at 10,000 to 100,000 solar masses, needs far fewer doublings to reach 1 million solar masses, and can do so within the time available at cosmic dawn. Another proposed pathway involves dense stellar clusters in the cores of early galaxies. If star formation in the center of a proto-galaxy produces an extremely dense cluster of massive stars, those stars can collide and merge with each other on timescales of just a few million years, building up progressively more massive objects. Eventually, the most massive object in the cluster collapses into a black hole that is already hundreds or thousands of solar masses, far larger than any ordinary stellar remnant. This intermediate mass seed then has a head start on the growth process, requiring fewer doublings at the Eddington limit to reach supermassive scales. Both pathways are physically plausible. Both are being actively modelled in simulations. Neither has been confirmed by direct observation, though the little red dots, whatever their ultimate nature, may represent a critical phase in one or both of these formation channels. If little red dots turn out to be young supermassive black holes surrounded by dense gas cocoons, they could be the observational signature of seed black holes in the process of rapid early growth. Identifying which seed formation pathway dominates, and whether both operate simultaneously in different environments, is one of the central open questions in early universe research. The story of how astronomers are explaining Webb's early galaxy observations is ultimately a story about the self-correcting nature of science. The initial results were surprising. The initial interpretations were sometimes alarmist, but within 2 to 3 years the community had identified the key sources of confusion, separated genuine signals from measurement artifacts, and developed physically motivated explanations that preserved the fundamental cosmological framework while revising the astrophysical details. This process is ongoing. New data arrive with every Webb observing cycle. New analyses refine previous results. New simulations test the proposed explanations against increasingly precise measurements. The picture that is emerging is not one of cosmological collapse. It is one of cosmological enrichment. The early universe was not the simple, dark, featureless place that the most conservative models suggested. It was a place where physics operated in regimes we had not fully explored. where the dense conditions enabled processes that are rare or absent in the modern universe, and where the first structures assembled with a speed and efficiency that continues to push the boundaries of our understanding. The models are catching up, the explanations are converging, but the universe, as always, had surprises in reserve that no simulation anticipated. The question now is not whether the explanations work, it is what the corrected picture actually looks like. What does cosmic dawn become when you account for bursty star formation, higher efficiency, active black holes, and all the complexity that Webb has revealed? The answer is a version of the early universe that is far more dynamic, far more dramatic, and far more interesting than anyone expected. There is a version of this story that would be easier to tell. In that version, Webb pointed its mirror at the beginning of time and found that everything astronomers believed was wrong. The Big Bang never happened. The universe is older than we thought. Physics is broken. Start over. That version makes for better headlines. It is also false. The real story is more subtle, more demanding of attention, and ultimately more profound. Because what Webb actually revealed is not that our picture of the universe is wrong. It is that our picture of the universe was incomplete in ways we could not have recognized until we finally had the technology to look. For decades, cosmologists carried a mental image of cosmic dawn that was shaped as much by the limits of available data as by the actual physics. When Hubble strained to see galaxies at redshifts of 10 and 11 and found only a few faint smudges at the ragged edge of its detection capability, the natural conclusion was that the early universe was a sparse and dimly lit place. Theoretical models reinforced this impression by predicting that star formation at those epochs should have been modest. The picture that emerged was one of gradual awakening, a slow sunrise, darkness yielding reluctantly to the first faint embers of starlight, building over hundreds of millions of years into the fully illuminated cosmos we inhabit today. Webb replaced that picture with something startlingly different. Not a slow sunrise, something closer to a sudden ignition. Within the first 300 million years, galaxies had already assembled stellar populations substantial enough to be detected at distances of over 13 billion light-years. Some had produced enough heavy elements to form dust grains. Others had grown supermassive black holes that were actively devouring material and radiating enormous amounts of energy. At least one had ionized a significant bubble in the surrounding neutral hydrogen, punching a hole through the cosmic fog hundreds of millions of years before the standard timeline said such holes should appear. And all of this was happening not in a single exceptional object, but across a population of galaxies that was far more numerous and luminous than anyone had forecast. The implications of this revised picture ripple outward through multiple branches of astrophysics, and they begin with the most fundamental question you can ask about the early universe. How fast can structure form? The standard answer, before Webb, was that structure formation followed a predictable hierarchy. Small dark matter halos formed first, merging into larger ones over hundreds of millions of years. Gas settled into these halos, cooled slowly, and formed stars at a regulated pace. The process was bottom-up and gradual, with each generation of objects providing the gravitational foundation for the next. This hierarchical model was not speculation. It was the direct output of some of the most sophisticated computer simulations ever run, validated against observations of galaxy distributions, clustering statistics, and the cosmic microwave background. It worked beautifully at moderate redshifts. It explained the large-scale structure of the cosmic web. It predicted the abundance of galaxy clusters at various epochs with impressive accuracy. What it did not predict was the population of luminous galaxies Webb found at the highest redshifts. The hierarchical model said that halos massive enough to host bright galaxies should have been exceedingly rare at redshifts above 12. The dark matter structures simply had not had time to merge into sufficiently large concentrations, and yet the galaxies were there, bright, numerous, and demanding explanation. The resolution involves multiple mechanisms working in concert, bursty star formation making galaxies temporarily brighter than their average luminosity, higher star formation efficiency converting a larger fraction of available gas into stars, active black holes contributing additional light that inflates apparent masses. These are all physically reasonable adjustments to the galaxy formation models. None of them require modifying the underlying cosmological framework. But collectively, they paint a picture of an early universe that was far more dynamic and productive than the smooth, gradual models had suggested. This is where the corrected picture of cosmic dawn begins to take shape. It is a picture characterized not by simplicity but by complexity, not by uniformity but by diversity, not by a single mode of galaxy formation but by multiple pathways operating simultaneously in different environments and at different scales. Consider the range of objects Webb has revealed within the first 500 million years of cosmic history. At one end of the spectrum are the spectroscopically confirmed galaxies at redshifts of 13 and 14. These are genuine stellar systems, powered primarily by star formation, producing ultraviolet light from populations of hot, young stars. Their luminosities suggest vigorous but not impossible levels of star formation, consistent with the higher efficiencies expected in the dense conditions of the early universe. They are surprising in their abundance and brightness, but they do not break any known law of physics. At the other end of the spectrum are the little red dots, compact enigmatic objects whose nature is still being debated, but which almost certainly involve supermassive black holes in some form. Whether these are conventional active galactic nuclei shrouded in thick gas cocoons, or exotic black hole stars representing a transitional phase in early black hole growth, or ultra-compact galaxies formed in rare low-spin dark matter halos, they represent a mode of early universe activity that had no precedent in pre-Webb observations. They are not galaxies in the traditional sense. They are something new, or at least something newly visible, and their existence tells us that the early universe contained a wider variety of luminous sources than anyone had imagined. Between these extremes lies a population of galaxies that are more massive, more chemically enriched, and more structurally developed than pre-Webb models anticipated, but not by margins that require exotic physics. They are the factor of 2 excess that remains after the little red dots are removed. They represent a genuine tension with the old models, but not a crisis. They are the objects that drive the ongoing revision of galaxy formation theory, pushing researchers to understand how gas cooling, stellar feedback, and gravitational dynamics operated differently in the early universe. This diversity is itself a key insight. Before Webb, the theoretical picture of cosmic dawn was essentially one-dimensional, small, faint, simple galaxies forming slowly in a dark universe. After Webb, the picture is multidimensional, bright star-forming galaxies, compact black hole-powered objects, chemically enriched systems with dust, galaxies carving ionized bubbles in the neutral hydrogen around them, spiral structures appearing far earlier than expected. The early universe was not a featureless desert waiting to be populated. It was already a complex ecosystem of diverse objects interacting with their environments in multiple ways. This complexity has particular significance for understanding reionization, the process by which the neutral hydrogen filling the post-recombination universe was gradually ionized by ultraviolet radiation from early stars and black holes. Before Webb, reionization was modeled as a relatively smooth process. Galaxies formed, produced ionizing photons, and slowly cleared the cosmic fog over a period stretching from roughly 200 million to 1 billion years after the Big Bang. The transition was expected to be gradual and roughly uniform, with ionized bubbles growing steadily around each source and eventually merging into a fully transparent universe. Webb's observations suggest the process was messier. The detection of Lyman alpha emission from JADE's GSZ 13.1 at a redshift of 13 implies that at least some regions of the universe were substantially ionized within just 330 million years. This is earlier than most models predicted for significant local reionization. If this galaxy cleared a transparent bubble around itself by that epoch, it means the sources of ionizing radiation at cosmic dawn were more powerful, more efficient, or more numerous than assumed. At the same time, thousands of galaxies from the epoch of reionization have now been identified by Webb across various surveys, and researchers have begun tracing individual ionized bubbles back to the specific galaxies responsible for creating them. This emerging map of reionization reveals a process that was highly inhomogeneous. Some regions of the universe ionized early, driven by particularly active clusters of galaxies. Other regions remained neutral for much longer, shrouded in fog while their neighbors were already bathed in ultraviolet light. The topology of reionization, the spatial pattern of ionized and neutral regions, was more intricate and varied than the smooth models suggested. This patchiness has observational consequences that future telescopes may be able to detect. The pattern of ionized and neutral regions imprints itself on the distribution of Lyman alpha emission across the sky. Galaxies in early ionized regions can show Lyman alpha emission. Galaxies in still neutral regions cannot. By mapping where Lyman alpha is detected and where it is absent, astronomers can reconstruct the geometry of reionization in 3 dimensions. Webb has begun this work. Future observations will refine it, potentially revealing the detailed structure of the transition from opacity to transparency across cosmic time. There is a broader lesson embedded in this story that extends beyond the specific details of luminosity functions and star formation efficiencies. It is a lesson about the relationship between prediction and observation in science, and about the particular dangers of extrapolating from known regimes into unexplored territory. Before Webb, the theoretical predictions for early galaxy properties were extrapolations. They took models calibrated against observations of galaxies at moderate redshifts of 2 through 8, where Hubble and ground-based telescopes provided extensive data, and projected those models forward to higher redshifts where no data existed. The extrapolation assumed that the physical processes governing galaxy formation at moderate redshifts continued to operate in the same way at earlier epochs. Star formation efficiency stayed at 1 to 3%. Stellar feedback remained equally effective at regulating gas collapse. The initial mass function of stars stayed the same. These were not unreasonable assumptions. They were the best guesses available in the absence of data. But they were still guesses, and the early universe turned out to be a different environment than the moderate redshift universe in ways that mattered. Higher gas densities changed the effectiveness of feedback. The absence of heavy elements altered cooling rates. The compactness of early dark matter halos created gravitational conditions without local analog. The prevalence of supermassive black hole accretion added a source of luminosity that the models had not anticipated in such abundance. Each of these differences was individually understandable. None required new physics. But their combined effect was to make the early universe more luminous and more complex than the extrapolations predicted. This is a recurring pattern in the history of astronomy. Every time a fundamentally new observational capability becomes available, it reveals complexity that the previous generation of models did not capture. Hubble did the same thing in the 1990s, when its deep field images revealed a universe far richer in distant galaxies than anyone had expected. The cosmic microwave background satellites did it in the 2000s, when precise measurements of temperature fluctuations revealed details of early universe physics that challenged and refined the existing models. Webb is doing it now, at the frontier of cosmic dawn, revealing that the earliest chapter of galaxy formation was written in a more elaborate hand than the models had assumed. There is something important to acknowledge about what Webb has not found. It has not found evidence that the Big Bang did not happen. The cosmic microwave background, the expansion of the universe, the abundance of light elements, the large-scale structure of the cosmic web, all the foundational evidence for the Big Bang remains as solid as ever. Webb's observations are entirely consistent with a universe that began in a hot, dense state 13.8 billion years ago and has been expanding and cooling ever since. It has not found galaxies older than the universe. The most distant galaxies Webb has detected exist within the first few 100 million years of cosmic history. They are young. They formed recently in cosmic terms. Their light has been travelling for over 13 billion years to reach us, but they themselves were newborns when that light was emitted. nothing about Webb's observations requires revising the age of the universe. It has not disproven the standard model of cosmology. Lambda CDM continues to provide the most accurate and comprehensive description of the universe's large-scale properties. The tensions revealed by Webb exist at the level of galaxy formation physics, not at the level of cosmological parameters. The adjustments needed to resolve those tensions involve refining our understanding of astrophysical processes, not overthrowing the fundamental framework. And it has not finished. This is perhaps the most important point of all. Webb is an ongoing mission with years of observations ahead of it. The discoveries described in this story represent the telescope's first 3 years of science operations. Deeper surveys, wider fields, longer spectroscopic exposures, and new observing programs will continue to push the frontier further. There are strong indications that even more distant galaxies exist, waiting to be found. The current record holder at a redshift of 14.44 may not hold the record for long. Some researchers have suggested that Webb could detect galaxies within the first 200 million years of cosmic history, possibly pushing into an era where the very first generation of stars was still forming. And Webb will not be working alone. A generation of new telescopes is approaching that will transform the study of the early universe from multiple directions simultaneously. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, carries a field of view 200 times larger than Webb's NIRCam. Where Webb studies the early universe through a soda straw, Roman will survey it through a picture window. Its wide-field infrared capability will discover hundreds of thousands of high redshift galaxies across enormous volumes of sky, providing the statistical power needed to measure the luminosity function at cosmic dawn with far greater precision than current surveys allow. Roman will not peer as deep as Webb into the faintest objects, but it will map the overall population of early galaxies with a completeness that no existing telescope can achieve. On the ground, the extremely large telescope, currently under construction in Chile's Atacama Desert, will bring a 39-meter primary mirror to bear on the early universe. That mirror collects roughly 35 times more light than Webb's 6.5-meter mirror, though it operates at different wavelengths and faces the limitations of Earth's atmosphere. The extremely large telescope's extraordinary light-gathering power will enable detailed spectroscopy of early galaxies that are currently too faint for Webb to characterize fully. It will measure the chemical compositions of galaxies at redshifts of 10 and above, determining which heavy elements are present and in what abundances. It will resolve the internal structures of early galaxies, mapping how stars distribute themselves within these ancient systems. And it will study the kinematics of early galaxies, measuring how gas and stars move within them, revealing whether they rotate, whether they are undergoing mergers, and whether they show the organized dynamics of mature systems or the chaotic motions of objects still assembling themselves. Other facilities will contribute complementary data. The Vera Rubin Observatory, also under construction in Chile, will conduct a 10-year survey of the entire southern sky, discovering transient phenomena and mapping the distribution of matter across cosmic time. The Square Kilometre Array, a massive radio telescope being built across Australia and South Africa, will detect neutral hydrogen emission from the epoch of reionization, directly mapping the cosmic fog that Webb's galaxies were embedded within. Together, these instruments will create a multi-wavelength portrait of cosmic dawn that no single telescope could provide. Each of these facilities will test the explanations that have been proposed for Webb's surprising findings. If bursty star formation is the dominant explanation for the brightness of early galaxies, Roman's large statistical samples will reveal the signature of that burstiness in the scatter of the luminosity function. If higher star formation efficiency is the key factor, the extremely large telescope's chemical measurements will show whether the heavy element abundances in early galaxies match the predictions of high-efficiency models. If little red dots are indeed young supermassive black holes in dense gas cocoons, future X-ray telescopes may detect the faint high-energy signatures that current instruments have not been able to confirm. What remains genuinely uncertain is substantial. The nature of the little red dots has not been definitively resolved. The relative contributions of bursty star formation higher efficiency, and active black holes to the overall brightness of the early galaxy population are still being quantified. The star formation efficiency at redshifts above 12 is poorly constrained by direct observation. The mechanisms by which supermassive black holes formed and grew so rapidly in the early universe are not understood. The topology and timeline of reionization are being mapped but are far from complete. The question of whether the initial mass function of stars was different at cosmic dawn remains open. Each of these uncertainties represents an active frontier of research. Each one is being addressed by teams of astronomers around the world using Webb data, ground-based observations, and increasingly sophisticated theoretical models. The pace of discovery is extraordinary. Papers appear on the preprint servers weekly. Results are updated, revised, and sometimes overturned within months. The field is in a state of rapid evolution, driven by a flood of data that has no precedent in the history of extragalactic astronomy. The comprehensive perspective published in Nature Astronomy in August 2025 captured the moment precisely. Drawn from the collective insights of an international assembly of leading researchers, it described what Webb had accomplished in its first years as nothing less than a transformative moment in cosmic research, one that was reshaping the field in real time. The early universe was being rewritten. One of the senior NASA scientists involved in the mission summarized it with a clarity that is worth absorbing. Webb is rewriting our understanding of how galaxies like our own Milky Way grew in the early universe and formed the elements that make up everything we know. With this telescope, we are literally seeing back in time to our own beginnings. That phrase, our own beginnings, carries a weight that is easy to overlook in the technical details of redshifts and luminosity functions. The first galaxies are not abstract objects of academic interest. They are the ancestors of every galaxy that exists today, including the one we live in. The Milky Way did not spring into existence fully formed. It grew over billions of years through a process of hierarchical assembly that began at cosmic dawn. The proto-galaxies that Webb is now detecting, those luminous clumps of young stars embedded in dark matter halos a few 100 million years after the Big Bang, were the building blocks. Over the following billions of years, these small systems merged with one another. Two proto-galaxies falling together under mutual gravity, their gas colliding and compressing, triggering new bursts of star formation, their dark matter halos interpenetrating and settling into a single larger structure. That merged system then collided with another and another. Each merger added mass. Each merger brought new gas. Each merger triggered new generations of stars that produced new heavy elements and scattered them into the growing galactic reservoir. The Milky Way carries the scars of this assembly process in its structure today. Stellar streams wrapping around the galaxy are the remnants of smaller galaxies that fell in and were torn apart by tidal forces. The stars in the Milky Way's halo, the sparse spherical population surrounding the disk, orbit on chaotic trajectories that betray their origins in separate systems that merged long ago. Chemical analysis of individual stars reveals distinct populations with different abundance patterns, fingerprints of the different proto-galactic environments in which those stars originally formed before being incorporated into the growing Milky Way. A major merger, roughly 10 billion years ago, with a galaxy called Gaia Enceladus, contributed a substantial fraction of the halo stars we observe today. That merger galaxy was itself the product of earlier mergers stretching back toward cosmic dawn. The chain of ancestry is direct and traceable. The proto-galaxies at cosmic dawn merged into larger systems. Those systems merged into still larger ones. Over billions of years, this process built the Milky Way we inhabit. The heavy elements forged in the earlier stellar generations, the carbon, oxygen, and iron produced by population 3 supernovae and their immediate successors, were passed forward through each merger, incorporated into new generations of stars, processed further, and passed forward again. The iron in your blood was forged in a star that may have lived and died billions of years before our solar system formed. But the very first atoms of iron in the universe were produced in the explosions of massive stars within the proto-galaxies that Webb is now observing. The connection is not metaphorical, it is physical. It is chemical. It is a chain of nuclear reactions and gravitational collapses linking the first galaxies at cosmic dawn to the composition of your own body. When Webb detects nitrogen in a galaxy 280 million years after the Big Bang, it is seeing the earliest known links in that chain. When it finds dust in a galaxy at redshift 12, it is seeing the first evidence that heavy elements had already begun condensing into solid particles, the same type of particles that would eventually coalesce into asteroids, comets, and planets in later cosmic epochs. When it observes a galaxy carving an ionized bubble in the surrounding neutral hydrogen, it is watching the early universe transform itself from an opaque fog into the transparent star-filled cosmos we inhabit. These are not distant, disconnected events. They are the opening chapters of the story that leads to everything we see when we look up at the night sky. Every galaxy visible through a backyard telescope descends from the objects Webb is now studying. Every star in the Milky Way traces its chemical heritage back through generations of predecessors whose earliest members formed at cosmic dawn. The first galaxies are our origin story. Understanding how they formed, how quickly they grew, and how they produced the building blocks of everything that followed is understanding the deepest roots of our own existence. The early universe was not simple. That is the central finding of Webb's first years of observation. It was not empty. It was not slow. It was not a featureless void waiting patiently for gravity to work its ancient magic over billions of years. It was a place where complexity emerged with a speed and vigor that has forced astronomers to reconsider what is possible within the known laws of physics. Galaxies lit up earlier than predicted. Stars formed more efficiently than expected. Black holes grew faster than anyone thought plausible. Chemical enrichment proceeded more rapidly than the models allowed. Reionization began sooner and progressed more unevenly than the smooth theoretical curves suggested. None of this broke physics. All of it expanded our understanding of what physics can do. The laws did not change, but our appreciation of what those laws produce when operating in the extreme conditions of the earliest cosmic epochs was fundamentally inadequate. Webb has corrected that inadequacy, not by overturning the framework, but by filling in a chapter that had been written in theory but never read in observation. There is a final thought worth sitting with. Every generation of astronomers that has built a more powerful telescope has discovered that the universe was more complex at earlier times than anyone anticipated. Every time we have pushed our observational reach further into the past, we have found that the cosmos was already busy doing remarkable things at epochs where we expected relative simplicity. This pattern is so consistent across the history of the field that it might qualify as an informal law of observational astronomy. The universe is always ahead of us. Webb is the most dramatic confirmation of this pattern yet. It was built to see the first galaxies, and it found them. But it also found that those first galaxies were more interesting, more varied, more chemically mature, and more structurally developed than the best theoretical minds in the world had predicted. The telescope did exactly what it was designed to do. The universe, as usual, did more than anyone designed it to. The story is not over. Webb is still looking. Deeper surveys are planned. New spectroscopic campaigns will confirm distances for hundreds more candidate galaxies. Future observations at mid-infrared wavelengths will reveal properties of early galaxies that are invisible at shorter wavelengths. And new theoretical models, informed by the data Webb has already delivered, will make sharper predictions that future observations will test. Somewhere in the infrared glow that Webb collects night after night, there may be galaxies even more distant and more ancient than any yet confirmed. The observational frontier at a redshift of 14 may soon move to 15 or beyond. Each step backward in time brings us closer to the moment when the very first stars ignited in a dark universe, transforming the cosmos from a cold, neutral void into the luminous, structured, chemically rich reality we inhabit. That moment has not yet been observed directly, but Webb has brought us closer to it than any instrument in human history. And the telescopes now being built, on mountaintops and in clean rooms and on launch pads around the world, will carry the search further still. The first galaxies did not arrive gently. They arrived with a brightness and a complexity that caught the scientific world off guard. They told us that the dawn of cosmic structure was not a slow, predictable process, but a rapid and multifaceted transformation that operated at the boundaries of what our models could anticipate. They told us that the universe is capable of building remarkable things in remarkably short periods, given the right conditions. And they told us that even after decades of extraordinary theoretical and observational progress, the cosmos still has the capacity to surprise the people who study it most carefully. That capacity for surprise is not a failure of science, it is the engine of science. It is the reason telescopes get built, the reason observations get made, and the reason the story of the universe keeps getting richer with every new chapter we manage to read. Webb has opened a chapter that will take years to fully understand, but the first pages are already astonishing. The early universe was not what we expected. It was more